Hey everyone, this is Jonathan from Chegg Tutors, and this lesson is about neutralization, which is the reaction of an acid and a base to give you water and a salt. So neutralization occurs when, let's say, the pH is very low. We have a low pH due to high amounts of H+. So in order to neutralize this acid, we add base to consume the hydrogen protons. So OH- will consume H+, to bring the pH back to neutral, to bring it up towards 7. So in a way you can think of it as bringing the pH back to neutral. It won't always be exactly 7, but it will be towards 7. Or you can think of it as the OH- ions are consuming or neutralizing the effects of the hydrogen ions. So it's the same thing if the pH is high, which means that the hydroxide ions are abundant, and we can neutralize the effect of the hydroxide ions by adding acid, and the H+, the hydrogen ions, will react with the hydroxide ions and neutralize their effects to bring the pH back down. So add H+ to neutralize. So this occurs during titrations when we have a beaker full of either acid or base. Let's say we have a beaker full of acid and we add base drip by drip to neutralize the acid and bring it back towards a neutral pH. And it's the same thing if we have a beaker full of base and we add acid to bring it back down towards a neutral pH. So let's first look at the neutralization between a strong acid and a strong base. So let's take a strong acid, hydrochloric acid, a strong base, sodium hydroxide. Like I said before, an acid plus a base will give you water plus a salt. Now what's the salt? Our water comes from here, OH- and H+, to give you H2O. And the salt comes from whatever ions are left over. So sodium, Na+, and Cl-. So our salt is thus sodium chloride. Now it's important to note that in these neutralization reactions, we're assuming that the reaction is at the equivalence point, say if we were doing a titration, which means that there are equal numbers of hydroxide ions and hydrogen ions. So they completely consume each other. There's no acid, no base left over. So they often ask what is the pH of a salt? Now, intuitively, you would say if you neutralize a strong acid and a strong base, they kind of cancel each other's effects and leave you to a completely neutral pH of 7, which is correct. But the reasoning behind this is that if we look at the breakdown of a strong acid and a strong base, so this goes to H+ and Cl-, and this is a completely irreversible dissociation. That's what makes it strong acid. And same with sodium hydroxide, which makes it a strong base. It completely dissociates. So that's the reason why it's a neutral pH, because Na+ and Cl- are extremely stable. They do not go in the reverse. This reaction does not go in the reverse direction, which it would if Cl- and Na+ were slightly reactive, but they're not. They're very stable as ions, so they don't react with anything. So there's nothing left over in the solution really to react with anything to cause any basicity or acidity. So that's why the pH is 7. But we'll look, when you have weak bases and weak acids being neutralized, you have some ions that are reactive because those reactions are reversible, and they'll react with water to form either hydrogen ions or hydroxide ions, which will lead to a slightly acidic or basic salt. So now let's look at the neutralization of a strong acid and a weak base. So let's use hydrochloric acid, and a weak base is ammonia. Now, you probably don't see that this would form water, but water is formed because it is a neutralization reaction, but we only really care about the salt. So here ammonia is going to grab a hydrogen ion from HCl, which leaves NH4 plus and Cl minus. This is your salt, ammonium chloride. So they often ask here, what is the pH of this salt? And to do that, we know that chloride comes from a strong acid, so it is a completely stable ion. It comes from hydrochloric acid. But ammonium comes from ammonia, which is not a strong base. So the reaction of ammonia with water to form ammonium and hydroxide is reversible, which means that ammonium likes to react with things. It's a reversible reaction. So if we have this salt in a solution with water, ammonium will react with water to give H3O plus ammonia. And hydronium is the same thing as H plus. And this is what causes slight acidity of this salt. So the pH won't be exactly 7 when we neutralize this acid with this base. Instead, it will be slightly acidic. So it'll be a little bit less than 7. And you can also do this intuitively. Since we're neutralizing a strong acid with a weak base, the acid kind of overpowers the weak base because it's strong and the base is weak. So it leaves with a slightly acidic pH of less than 7. So now let's look at the neutralization between a weak acid and a strong base. So you can probably assume by now, since we're titrating a weak acid with a strong base, the pH will be slightly basic because the base here kind of overpowers that weak acid. So let's take our weak acid, we'll use acetic acid, and neutralize it with NaOH to give water plus our salt, which will be sodium, and acetate. Liquid here, put AQ here. And what's going to happen here? Well, sodium is stable. It doesn't react because it comes from a strong base, sodium hydroxide. However, this species comes from acetic acid, which is not a strong acid. So those reactions are reversible. Acetate can react with water because the breakdown of acetic acid is reversible. So acetate likes to react with water. Reacts with water. So acetate will then react with water to give CH3 COOH plus OH minus. It's going to grab a proton from water to form OH minus because acetate is a weak base. So this OH minus causes slight basicity of the salt. So the pH is going to be a little bit higher than 7 of this salt after the neutralization reaction. So it's higher than 7, but slightly. And the same thing as the last problem, they're only slightly different than 7. They're not exactly 7, but they're only slightly different. So now let's look at the neutralization reaction of a weak acid and a weak base. So let's use hydrofluoric acid as our weak acid. And as our weak base, we'll use ammonia. And this reaction is taking place in water. So the ammonia is going to take a hydrogen ion from hydrofluoric acid to form ammonium and F minus fluoride ions. So this is your salt, ammonium fluoride. And now we can ask, what is the pH of this? Well, we have both species coming from weak bases and weak acids. So this comes from a weak acid. So that reaction, the dissociation of hydrofluoric acid, is reversible. So F minus likes to react. So this is reactive. But so is ammonium. Ammonium likes to react with water too, because it comes from a weak base, so it's also a weak acid. So both species will react with water. So we'll have two reactions taking place from this salt. We'll have NH4 plus H2O to give H3O plus ammonia. And we'll also have F minus reacting with water to give OH minus and hydrofluoric acid. So both of these species are going to react with water to give hydrogen ions and hydroxide ions. So what's the pH? Well, here we have to look at the Kb's and the Ka's of both species. So the Ka of ammonium is 5.56 times 10 to the negative 10th. And the Kb of fluoride ion is 1.52 times 10 to the negative 11. You can do that by doing Ka times Kb equals Kw and use the Ka of hydrofluoric acid. So obviously the Kb of fluoride ion is much smaller than the Ka of ammonium. So that means fluoride does not like to form products as much as ammonium does. So that means that there will be less OH, so the concentration of OH minus will be less than H3O plus, because the Ka of ammonium is bigger, so it forms more of its products than fluoride ion does. So hydronium ion concentration will be greater than hydroxide ion, which means that the pH will be less than 7, because more hydronium ions and OH minus means that you're more acidic. So it is slightly acidic. So I hope this helped, and hope it taught you about neutralization and how to determine the pHs of certain salts. And my name's Jonathan, and I'm on Chegg Tutors.